We've been looking at how delta H can be measured experimentally using calorimetry, or how we can infer it through Hess's law by combining other chemical reactions with known delta H's. We can also calculate it from standard enthalpies of formation. So delta H is the change in enthalpy. And we're not interested in an absolute level. That's not really meaningful. We're interested in the change. And so we can define zero as anywhere that's convenient. And you think about altitude. How did they decide what was zero altitude? Well, zero altitude is sea level, right? Because that's convenient. It's the same everywhere, right? So they chose something convenient. So here, we're going to measure enthalpy changes relative to pure elements in their standard states. So we're going to use that as our zero reference point. So what are the standard states? For a gas, that means that you have the pure gas at 1 atmosphere of pressure. For a liquid or solid, that's going to be the pure substance in its most stable form at 1 atmosphere of pressure, and the temperature of interest, which is usually 25 degrees Celsius, which is considered room temperature. If you have a substance in solution, it is the substance with a concentration of exactly 1 mole per liter. So that's what we define as the standard states. Standard enthalpy change, delta H, with this degree sign here, and that means that we're talking about standard states. It's the enthalpy change when all the reactants and products are in their standard states. And if we talk about the standard enthalpy of formation, and throw an F in here, that's the enthalpy change for the reaction that forms 1 mole of the substance from its constituent elements. It's also called the standard heat of formation, because we often use the word heat and enthalpy somewhat interchangeably. So the elements have to be in their standard states, and this is just a reminder, elements in their standard states, the heat of formation is 0, because that's how we decided to do it. Enthalpy changes are measured relative to elements in their standard states, just like we measure altitude relative to sea level. So this is a table showing a very small number of standard enthalpies of formation, or heats of formation. So here we have the chemical formulas, and these are the different elements. So here, bromine, like if you wanted carbon, there's a bunch of carbon-containing compounds. There's also carbon as an element, the graphite and a diamond. So those are 2 forms of solid elemental carbon. The standard state is the one with the delta HF of 0. So you'll notice there are some zeros in here. Those are all the elements of their standard states. If we want to know the heat of formation for water, we'll go look under oxygen. And so for water in the liquid state, the heat of formation is negative 285.8 kilojoules per mole. So we just go look these things up. So we use them with formation reactions. So if we want to know what the standard enthalpy, well, we look up the standard enthalpy of formation for the compound, such as methane. We look it up, it's minus 774.6. And then we can write a chemical equation representing that, where we're forming 1 mole of the product from elements in their standard states. So carbon as graphite, and 2 moles of hydrogen gas. Sometimes you might not be sure what the standard state is. Well, then you go look in that table, and there's another bigger one in Appendix 2B at the back of your book. You look for that element with a heat of formation of 0. That's the one that's the standard state. So this is defined as the amount of energy for 1 mole to be made. And so these formation reactions are always written so you have 1 mole of product. That means we'll sometimes see fractions in the reactant coefficients. So we're going to look at writing the formation reaction for carbon monoxide gas. So carbon monoxide gas, and there are 2 elements in this compound, carbon and oxygen. And so we need to identify their standard states. So if we look up carbon, the one with delta H being 0 is graphite. And so this is carbon as a solid and the form of graphite. Oxygen's standard state is the diatomic gas. So this would be O2 gas. And then we have to balance the equation. We need to keep the coefficient of the product as 1. Normally we would balance this. We say, well, there's 2 oxygens here, so we'll put a 2 here and we'll put a 2 there and it'll be balanced. But this coefficient must be 1. So now we're going to use fractions when needed. So 1/2 of O2 is 1 oxygen, right? And this is 1 carbon, and so together those would make carbon monoxide gas. And then you look up the heat of formation in the table. So under carbon, here's carbon monoxide gas. The heat of formation is negative 110.5 kilojoules per mole. So write equations for the formation of sodium chloride and lead 2 nitrate from the elements in their standard states. Include the values of delta HF for each equation. Well, let's do the first one first. This is going to be our product, so I'm going to write that at the end. NaCl as a solid. So then we identify what elements are in the compound. Well, there's sodium and there's chlorine, right? Now let's just guess and check in the table. What do you think the standard state of sodium is? Well, solid. One way we can tell that is by looking at the colors of the element symbols. And we see that sodium is black, meaning it's a solid at room temperature. What's the physical state of chlorine? It's a gas. Are either of these, sodium or chlorine, are they diatomic elements? Chlorine's a diatomic element, so it's probably Cl2. And then we can go check that. So we look under chlorine, and it does show Cl, gas, but that doesn't have a heat of formation that's 0. It's Cl2 that has the heat of formation 0. And under sodium, you see NaS is the 0. So we've got our standard state elements, and then we balance the equation. How can we balance this? We could put a half in front of this because we only need 1 of the chlorine atoms. So we're going to take half that molecule to make this. And in terms of molecules, that doesn't make any sense. But if we're talking about moles of molecules, then it's perfectly fine. And so then we're going to look up delta H for this. So under sodium, sodium chloride, solid, negative 411.2. See that over here? I can't point at it or I'll mess up, I'll lose all my writing. That's kilojoules per mole. That is the number I just said, isn't it? 411? Okay. I'm not sure what day it is. Any questions about that?
So how can something that, I guess, how does it go from 0 to all of a sudden having a release of energy?
That's a great question. That's a great question. The reason that this is releasing energy is because strong bonds are being formed and weak bonds are being broken. So there's a bond between these two chlorine atoms in this molecule. That has to be broken. That requires you to put energy in. But here, when we form this ionic bond between sodium and chloride ions, that's very strong. And so that results in the release of a lot of energy. And we will talk a little more about that later. So let's look at the other one. Again, I'm going to write the formula for what we're making over here. And this is a solid. So PbNO32. And then this is the one time where you do just get to pick it apart into its separate elements. People try to do that with solubility of ionic compounds, and then you can't. But here you get to do that. So there's 3 capital letters here, right? We've got Pb, and we've got N, and we've got O. Well, what's the standard state of lead at room temperature? It's a solid, like lead pipes. How about nitrogen? That's a gas. And is it diatomic? Yes, it is. And then oxygen, what about oxygen? It's also a diatomic gas. So we've got our standard states. So there's 1 lead and 1 lead. How many nitrogens are in this formula? 2, right? So I've got 2 nitrogens over there. That's good. How many oxygens are in the formula? 6. So I need to put a 3 in front of O2 to make it balanced. And then I have to look up delta H, which I'm pretty sure, if I remember correctly, is not in the table. Yeah, lead's not in there. Oops. So we would have to go look it up in the back, in the larger table, and the heat of formation for lead nitrate is negative 451.9 kilojoules per mole. You can find that in the appendix in the back. Oh, actually, here it is. I forgot. I stuck that in there because I got frustrated with not having the number. Here it is, right here. So you can see this is just part of the table back there, but it gives a lot more compounds than the little one that's in Chapter 7. So the heat of formation corresponds to the formation of a compound from its constituent elements in their standard states. Taking the elements, making the compound. What if we do the opposite? What if we take the compound and take it apart into its elements in their standard states? What's the heat of reaction for that? When we reverse the reaction, we change the sign, right? So it's the same number, but we just change the sign. So using this idea, we can calculate the enthalpy change of any reaction by, just in our minds, decomposing all of the compounds into their elements in their standard states and forming the products. So any reactants we'll take apart into elements, and we can look up the heat of formation for that. Taking it apart, we change the sign. The products, we're making them from the standard states, and so then we also look up their values and use them as is. So any chemical reaction can be written as the sum of formation reactions or the reverse of formation reactions. And so a shorter way to look at this is here. So the standard heat of reaction is going to be the sum of the heats of formation of all the products. If there are coefficients, if you make 2 moles, you're going to have twice as much energy change. So each of those has to be multiplied by a coefficient. Those are all going to be the correct sign or the posted sign for delta H. And then we're going to subtract the heats of formation for the reactants. We're subtracting those because those are negative because we're taking those apart. Taking the reactants apart, and then we're forming the products. We can also look at this in terms of Hess's law. We have this energy diagram here. What we're looking at is this equation, well, this one up here, C4 plus 2O2, making CO2 and water, combustion of methane. So here's our reactants. They have this level of energy. And when we make the products are lower in energy. So what we're doing is we're imagining that we take this methane and we break it into its elements. So if I take methane, that would be these guys, right? Do we need to do anything to oxygen to get it into its standard state? No, because it's already in its standard state, right? So this difference here is we take the heat of formation for methane and we change the sign. And so that gives us plus 74.6. This is the heat of formation, the formation reaction, and the heat of formation for methane. Now we have elements in their standard states, and we're going to make these products. One of the products is CO2. So when you make CO2, you use 1 carbon and 1 oxygen, and it releases 393.5 kilojoules per mole. So that's how much energy would be released when we made the CO2. And then we can make 2 water molecules, or 2 moles of water, H2 plus O2. So H2 plus 1/2 O2 gives us 1 H2O. So we're taking that and multiplying it by 2 because we're making 2 moles, and that's negative 241.8. And you can add those together, and then you get the heat of formation, or the standard enthalpy change for the chemical reaction. Now that math equation that we looked at with the big sigma sign, so what that basically is saying, is our standard heat of reaction. So we're going to look at our products. So one of our products is CO2. So we're going to use the heat of formation, standard heat of formation for CO2. And water, standard heat of formation, actually a little more space, standard heat of formation for water. But we're using 2 moles of that, so we multiply that by 2. Those are my products. And then I'm subtracting the heats of formation of my reactants. So the heat of formation of methane and 2 times the heat of formation of O2. Except this is an element in its standard state, and so that's 0. So we don't need that one at all. So heats of formation of the products minus the heats of formation of the reactants. Just like delta T, it's the final minus the initial. It's the final enthalpies minus the initial enthalpies. And we can go look these up in a table. Here we don't need to because they were given to us down here. But for this reaction then, we've got the heat of formation of CO2, which is negative 393.5 kilojoules per mole. And we have 2 times the heat of formation for water. So plus 2 times negative 241.8 kilojoules per mole. And we've got that whole thing, and we're subtracting the heat of formation of methane, negative 74.6 kilojoules per mole. So negative 393.5 plus 2 times negative 241.8 minus negative 74.6, negative 802.5 kilojoules. This here?
Yeah.
It's because I didn't have enough space to put it all on one line.
Oh, okay.
I'm text wrapping.
Got it.
Yeah. Yep, that's all. So this is all one equation. This minus that, and then this is all one equation. This minus this. And this is our answer. Any questions?
Well, that sign change usually have to go within the
Mm-hmm.
in case you just didn't know.
So when you do the equation this way, think final minus initial, right? Look up the heats of formation for the products, and then subtract the heats of formation for the reactants. So here, this is negative. The heat of formation is negative. And when we're subtracting it, that changes the sign. Okay? You can think of it this way. You can think of these reaction formation equations and how to put them together, like Hess's law, and get the answer we want. But I think that's a lot more complicated. It's the final minus the initial. Any other questions? The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic, rather spectacular to watch. Use standard enthalpies of formation to find the standard heat of reaction for the thermite reaction. So what we want to do here to find the standard heat of reaction is we're going to find the heats of formation of the products, and we're going to subtract the heats of formation of the reactants. Are any of these elements in their standard states? Yeah, iron and aluminum, right? This is an element in its standard state. Element in its standard state. Its heat of formation is 0. So that one's 0, and this one's 0. So then I have one product and one reactant left. And they both have coefficients of 1. These have coefficients of 2, but it doesn't matter if you multiply 0 by 2, it's still 0. So what we want here is the heat of formation for aluminum oxide, and we're going to subtract the heat of formation for iron 3 oxide. Where do we find these numbers? We have to go look them up. So here we have Fe2O3. Now this table has delta H, delta G, and S. So make sure you're looking at the right column. It's the first column. So for Fe2O3, it's minus 824.2. I'm going to write that on the board. 824.2. And then the other one we needed was aluminum oxide, right? So that's way up at the beginning, negative 1675.7. Okay, now we can go back to our problem. So we looked up the heat of formation of Al2O3, and I wrote it on the board because my short-term memory is questionable sometimes. Minus 1675.7 kilojoules per mole, and we're going to subtract the heat of formation of the reactant, negative 824.2. Now, of course, you can combine those negative signs, right, and make it a positive, but you don't need to. A scientific calculator has a subtraction button and a negative sign button. So I'm just going to type this in right as it looks. So negative, not the minus sign, but negative 1675.7 minus negative 824.2, and I'll let the calculator do the thinking for me. Negative 851.5. Any questions? Here's another one. Back to the chemical hand warmers. Chemical hand warmers produce heat when they're removed from their airtight plastic wrappers. The reaction is 4Fe plus 3O2 makes 2Fe2O3. Calculate the standard heat of reaction for this reaction and calculate how much heat is produced from a hand warmer containing 15.0 grams of iron powder. So, calculating the standard heat of reaction, it's going to be the heats of formation for the products minus the reactants. So, the product is Fe2O3, and then we're subtracting the reactants. But what makes this easier? Those are elements in their standard states, and so those are 0. 0 and 0. So we already used the heat of formation of Fe2O3. It's conveniently here on the board. What did I forget? I forgot the coefficient, right? So it's the coefficient times the heat of formation. So 2 times negative 824.2, negative 1648.4, kilojoules. So that's the heat of formation for this equation. Sorry, the heat of reaction. What really happens with the units here is I'm taking 2 moles, right? That's what this means. 2 moles of this times the standard heat of formation, which is this many kilojoules per mole, and the moles cancel out. And so this number then goes with this specific equation, chemical equation. So that's the first part. How can we figure out how much heat's released when 15 grams of iron powder reacts? Grams to moles to kilojoules, right? It's a variation of grams to moles to grams. Because we're doing heat here, we don't need a second mole in there. So we can go from 15 grams of iron to moles of iron to kilojoules. And so we're going to get our units all to cancel out. The kilojoules, this is minus 1648.4 kilojoules for how many moles of iron? Iron. The coefficient, right? There's 4 moles of iron in this equation. So this is the amount of energy released when 4 moles of iron reacts. And then we need the molar mass of iron, which is 55.85 grams. So 15 divided by 55.85 times negative 1648.4. Bless you. So negative 442.72, blah, blah, blah. Here, the starting mass is only 3 sig figs. So that's going to limit this to 3 sig figs, 443 kilojoules. Now, this is the number that we get when we do the calculation. The question here is calculate how much heat is produced. This is like saying, well, I spent negative $10 on my drink at Starbucks, right? I mean, they paid you to get a drink? What? No, I spent. I don't need a negative sign because the word says the direction. The money left me, right? So here it says the heat is produced. We don't need a sign. And so the correct answer would be that 443 kilojoules of heat is produced. That can get a little confusing sometimes. I will not try to trick you with that on an exam. Okay. But if you're doing a homework problem or something and the negative signs just seem to come and go, like what the heck? That's probably it. Because if there's a word that gives us the direction, then we don't use the negative sign. Any questions?
I need to divide by the 4 moles of iron.
I did. I told you last week, I forget to do that. Thank you. I forgot to divide by 4 moles of iron. It's just, sitting there. Okay, we can fix this. Thank you very much for telling me. So, negative 110.68, which would round to negative 111, or 111 kilojoules are produced. Any other questions? Problems?
The kilojoule is a mole you are able to skim because of the
Well, yeah, so this delta H here goes directly to each of these. So, I could put in, moles of iron to moles of this and then go to kilojoules, but I don't need to, right? So let's not put extra stuff. Any other questions? Extra stuff is only good in Oreos.